Another important thing to know about the packed RBD object is that you can carry attributes into the DOP network and use those attributes to influence the behavior of the simulation. So as an example, just to make it really obvious, if I put, let's say, a color attribute on our points here, I say @cd is equal to curly brackets, and I say a color of red, so 1, 0, 0. And I set that to the points. Everything is red. Going into the simulation, now everything is red here as well. With the course, you'll find this Houdini RBD packed object attributes sheet. Sounds kind of fancy, but really all this is a list of attributes that can be used and understood by the rigid body solver, with some brief definitions to say what that's all about. So in this case, we want to find something that affects the activation of those stones towards the bottom of the wall. This will prevent the stones from collapsing. So here we have this I@active, which is an integer attribute, and that toggles between the object being active, and this basically says that being active means that this will be affected by other objects and forces within the scene. So if we set that to 0, and let's say we have the bottom of the wall, well, that's going to prevent the gravity, the force of gravity, from affecting those bottom stones. And so this is how you want to control parts of the simulation using this worksheet. If you can go through here and figure out what some of these things do, you can control the various behaviors of what's happening on the objects. And so in this case, if I set I@active equal to, let's say, 0, what you'll notice is that nothing happens in the simulation. The first frame takes a little while because it makes all those convex holes, but then once it gets done with that, nothing is active, so nothing happens. And if we want to go and fix, let's say, that problem where our wall is crumbling because of gravity, we can isolate that to a certain region of this wall and then source that into the DOP net to prevent that from happening. So here's what that might look like. If we use a group and we group a bunch of points, let's call this our active toggle. Group name is $OS. We'll do this over points and then change the base group to keep in bounding regions. So a bounding box is made. Anything in the box is part of the group. So we'll go right about there and give ourselves a bit of room to start. We can always bring this down. But we'll end up doing something right about there. And then also check on this include partially contained entities. Okay, so now that we have that, if we take this wrangle, we can just run that over the group if we want. But it's not going to be the best way to do that because even though we've selected things down here, what you'll notice is that the top pieces won't be active. And I know that because I've already set up this visualizer to show the active value. And if we look up here, that active value is at 0. So again, this marker, it says active. Right now at top, it's a 0. So, and that's because this attribute wasn't created in the first place. And because of that, that's why it just defaults to 0 if the wrangle never thinks about it. So instead of doing it that way, let's try something else. We'll start off by getting rid of this group field right here, and we will initialize our attributes up here to something else. So let's actually just take our active here to a value of 1 to start, and then we'll say if, we'll make a conditional statement saying if at group underscore active toggle is equal to a value of 1, curly brackets, then we can set I@active to 0. And now at the bottom here, this is 0. At the top, that's 1. And just to show what we've affected, let's also change the color here to green. So at CD is equal to 0, 1, 0. There we go. So we've affected those areas right there. Now if we go to our sim, what you'll notice is that towards the bottom here, the active is 0. At the top, the active is 1. And that will prevent our wall from crumbling because of gravity. What was happening before is that the constraints were having force applied to them towards the very bottom, where the green stones are at right now. And that force propagated upwards into the entire network. And because of that, that was causing all the constraints to break and causing the whole wall to crumble. But now, since we have the bottom here deactivated, that force never gets applied to the constraints and never propagates through. And so that's why the wall is able to hold up, even though the top areas are active. This will, I think, make a little more sense, or I guess be a tad bit more clear once we have Eugene brought into the picture. So let's do that. Let's go find our friend Eugene. He is living over in the object area. So OBJ, Eugene, and we actually never made an out for him, so let's go do that. All right, here he is. Let's use an unshattered version of Eugene, by the way. So we'll just take this and say Eugene out. There we go. And he's looking a little small right now, so let's also use a transform to scale him up. So we'll go maybe right about there. Okay, we'll have him blast through the wall facing this way. So we'll go maybe right about there. Situate him in the middle. And now he's almost ready to go. Let's merge this in with the third input. And just to add a little bit of spice to the mix here, let's go ahead and bring Eugene over there so that we're organized. And also, I want him to do a front flip as he breaks through these rocks. It's going to be this crazy acrobatic performance like you've never seen. Create a point wrangle, and the way we're going to do this is we're going to use a combination of velocity and angular velocity to basically source in the movement info as he goes through the sim. So, starting with velocity, v at v is equal to, let's say, a channel vector, and we'll call this one our velocity, times another channel here called velocity underscore scale. Go ahead and click this parameter, and here we go. So, velocity scale. This will start at 1. The actual velocity, though, we want to go in the z direction. So let's start with 5, and in the y direction, we'll do 2. So we'll start there, and just to be sure that everything is working, let's also try to bring him into the simulation. But before we do that, let's also be sure that Eugene is packed geometry. So middle mouse here, we do not have packed geometry yet. So pack that. There we go. And once we have that, now we can go to our DOPNet. And I've actually already set up this RBD packed object. It's set to third context geometry. And the key to this here, to get the velocity working, is in the initial state, you need to go down and check this little box that says inherit velocity from point velocity. That will read in this information right here. So once we do that, and we go forward a few frames, let's see what happens. And boink. Okay, well, little disappointed, honestly. We need some more juice. So, back to the point wrangle, and we will go to velocity scale of, let's say, 5. Let's try that and see what happens. And off and away. Whoa, look at that. So it's getting somewhere. We're not there yet. Eugene is not going through the wall, and I'm not sure what that whole secondary explosion was all about. But we are getting somewhere. Now we're starting to actually break down this top area. To test this out though, it's going to take a while because every single time we try the simulation, we have to build out this entire wall. So let's go ahead and actually disable that for a minute and go to our point wrangle here and mess around with something else like angular velocity. So angular velocity is also a vector, v at, and we're going to use w on this, equals another vector channel that we'll call our angular velocity. And same deal here, we will multiply this times a angular velocity scale. Okay, with the angular velocity, I believe what we want to do is we want to set this to a high value. Let's say 20 for the time being, and then the scale needs to be at 1. Okay, let's see what happens when we do this. Oh, there he goes. So, that's better. Okay, that's definitely behaving in a front flippy kind of way, which is exactly what I want. Let's turn that down though. Maybe like 10. Yeah, okay. I think 10 is starting to get somewhere. Also, we want to use another node in here. Let's go ahead and use a drag force. So we'll use a pop drag and also a pop drag spin. So the drag spin affects angular velocity, the drag affects regular velocity. And that will just make it feel a little bit more natural as he goes through the air. So if we plug that into the post solve, let's take our pop drag 0.075 and our pop drag spins maybe like 0.1. Now if we press play, we get something like that, which looks a lot better in my opinion. Okay, so I believe that Eugene is fairly set with this. Maybe we'll go a little more in the front flip. So 15 instead of 10, split the difference. Yeah, that's really cool. But alas, there is still more work to be done. Also, I haven't really explained what the active attribute's all about. So in the next video, let's take a deeper dive into the differences between active versus static versus animated and deforming attributes.